So we're going to have families of exponential sums. We'll be interested in the distribution of these exponential sums. And in trying to solve the distribution problems for these exponential sums, we need a formalism, which turns out to be that given by these complicated tannakian categories. And in order to transform very abstract statements that we will deduce from this formalism into actual concrete statements, where we say such and such a sum is actually distributed according to such and such a measure, we need to know the measure, and to compute the measure, one tool we can use turns out to be closely related to Sidon set. Okay, so I'll start by explaining what the three objects are quickly. So what kind of exponential sums are we looking at? So we're looking at families of exponential sums over finite fields. And by families, I emphasize that means there'll be many different sums with some parameters, and we're going to look at their distribution. So the basic examples. So it's usually convenient to normalize them in such a way that the line or the veil bound will tell us that they are bounded. So we have the Clusterman sums parameterized by A. So the parameter in this case belongs to FP. It's an abelian group with addition. We could have a multiplicative character sum, let's say with some cubic polynomial inside. And so here you see, because I fixed the cubic, instead of taking coefficients, for instance, AX plus B, we'd have a family parameterized by A and B here. The cubic doesn't change. What changes in this case would be the character chi, which as usual is a multiplicative character. So when I write chi, that's usually what I mean. And a bit later, we will have families where we could have two types of parameters. So we could have chi of x, e of ax plus x bar over p. So this would be a family with two parameters, kind of one multiplicative, one additive. And these, I guess, could be or are called Clusterman sums. Although maybe Salier sums is usually maybe reserved when chi is the real character. So here the character will really vary among all the characters of FP star. So these are the exponential sums, and we're interested in how they are distributed when the parameter varies. And each finite field gives us only finitely many points. So usually we cannot say much about the distribution of finitely many points. So we typically replace the parameters by the corresponding ones over extension fields of FP, so FP to the n, and let n goes to infinity. The question is then distribution of these sums asymptotically. Okay. One could also do the situation where P is a prime number and we let P go to infinity. This is actually maybe for many arithmeticians, many number series more natural. As often the case when we use algebraic geometry, it's also harder. So we start with the easier case when we increase the degree of the finite field with respect to the base field FP. Okay, so these were the exponential sums. Now let's go to Sidon sets. So this is a very simple looking definition, which goes back to Sidon. So actually, maybe I'm mispronouncing the word. So Sidon was a Hungarian mathematician. And in a paper in 19...
You are doing well. You are doing well.
Okay, I think it's one of the easier Hungarian names to pronounce. So in a paper from 1931, in order to prove a nice result on Fourier series of periodic functions, Sidon used certain sets of integers. So we used basically powers of a fixed integer at least 2. But then at the end of his paper, he observed that what he used of this set is a very simple property, which is satisfied by other sets, including much denser ones. So to give a definition which works in any abelian group, because I'm going to be using more general abelian groups than the integers, which would be the case that Sidon considered. So you take an abelian group, capital A, doesn't have to be finite. Most of our cases would be finite, but it doesn't have to be. So a Sidon set in A. Well, I should mention also that there's actually 2 types of Sidon sets that exist in harmonic analysis. It's very confusing. It's even worse than the Bernstein polynomials. There are 2 types of Bernstein polynomials, but at least there are 2 Bernsteins. Whereas the Sidon sets, there are 2 Sidon sets, and they are named from the same mathematician. But the Sidon sets that we have here are kind of the more combinatorial ones. That means that if you have 2 elements in the set, so if the condition x1 plus x2 equals x3 plus x4 with all variables in the subset S implies that the 2 variables are permutations of each other. So let's say x1 must be either x3 or x4. That's one way of phrasing it. So that's the definition of a Sidon set. Oh, I seem to have lost, sorry, the beginning of my slides. Okay, so let's look at quick examples. So basically the example that Sidon used would be something like 2 to the power n, or 3 to the power n for any integer. That's an easy example. That's a very sparse Sidon set in the sense that the number of elements up to a bound is just logarithmically growing with the bound. Erdős and Turan quickly produced examples which were essentially optimal size, that they contain almost square root of n element up to n, which is more or less the best one can hope for. Here is another example that's quite dense. It's usually attributed to Ruja, but I recently learned from Sean Eberhard that this was found independently a few years before Ruja in a paper of Spence, who's a kind of more like algebraic combinatorialist. And it's remarkably simple. So it's the diagonal, but you view it as a subset of the abelian group K star cross K, where K is an arbitrary field. So this is a Sidon set because if you write down the equation in terms of this abelian group with multiplication on the first component and addition on the second component, you see that the equation implies that the 2 coordinates are the solutions of the same quadratic equation, so they have to be permutations of each other. So that's a very, very simple example. And if you take in FP, so K equals FP, this gives about, this gives exactly P minus 1 elements, so a set with P minus 1 elements in a set with, so in a group with P times P minus 1 elements. So it's very close to the square root. It's essentially, it's almost optimal. So let me give another example which is not relevant. So this example is very relevant to my talk. The next one is not really relevant, but it's very nice, and I want to mention it. So because in some sense that might be the most interesting thing that you might want to remember. So it's apparently due to Ellenberg Venkatesh, who told it to Ben Green, who told it to Eberhard and Manners. And that's from Eberhardt and Miners that I learned of it recently. It's really quite beautiful. So you take D, a fundamental discriminant of an imaginary quadratic field, and you look at in the ideal class group. So the abelian group is the ideal class group. So size of A is something like D to the 1/2 with small fluctuations. And you take as Sidon set the prime ideals. So the ideal classes which are represented by a prime ideal of norm, let's say strictly less than D to the 1/4. Absolute value of 20. So the usual kind of computation, which says that the norm of an element cannot be less than D unless the imaginary part, the B in the A plus B square root of D is 0, will show that this in fact is a Sidon set. Okay. And in terms of size, under GRH at least, it's fairly close to D to the 1/4, and therefore is also relatively good as far as the size of Sidon sets can be concerned. Okay. And maybe I will mention more examples later, but now let me go to the third ingredient of my talk. So we have the exponential sums, we have the Sidon sets. Now we have to look at tannakian categories. So these are objects which are quite complicated algebraically, but in a sense, this is just a way, which I will not try to describe precisely how, at least not now, to describe a group. Okay, so it's just another way of thinking of groups, and without trying to give a definition, which I probably would not succeed in doing actually in a correct way. So one way of thinking about it is to look at all the linear actions of the group on vector spaces over a fixed field, 5-dimensional vector spaces over a fixed, over C, let's say. So why should that be a useful way of thinking about a group? So we'll hopefully view an example where this turns out to be the only way to talk about a certain group. But for me, kind of an analogy is I kind of think that if you want to describe 5-dimensional real vector spaces, you could think it's a tuple of real numbers. And some of, I think, of the earliest axiomatics of vector spaces were based on this idea. It's just a tuple of vectors, a tuple of real numbers. Or you can give an abstract definition with an abstract addition and abstract scalar multiplication, satisfying some conditions. And then you have a theorem that tells you that there is a basis in any vector space, and you recover the first condition from the second, more abstract one. But there are lots of objects which kind of trivially satisfy the second condition, that satisfy the axioms of vector spaces. For instance, the set of solutions to a linear differential equation. It's obvious that it is a vector space in terms of addition and multiplication. And so you get a basis out of an abstract theorem. So here the situation is quite a bit more involved maybe, but it's still the idea that sometimes a fairly concrete, simple mathematical object, in our case a group, is easier to recognize by looking at a more abstract definition. Okay. So useful definition, it's not really a definition of a group, because sometimes we can construct groups this way. Okay. And part of my talk is to try and show how indeed sometimes one can construct groups interesting groups with this kind of abstract thing. Okay, so now having introduced the three characters, exponential sums, Sidon sets, and tannakian categories, let me talk about the equidistribution of exponential sums. Because this is, in the end, this is the kind of statements we're going to want to prove. And I'm going to go through the history of the main theorems about the equidistribution of families of exponential sums over finite fields. So everything in terms of actually proving real non-trivial statement begins in that case with Deligne. So early 1980s, his second proof of the Riemann hypothesis for finite fields. He proves a statement which essentially says that the slogan can be thought this way. So any family of exponential sums parameterized by the points of an algebraic variety. So to simplify, let's just think of family parameterized by a tuple of elements in a finite field. And let's look at the extensions of this finite field. So this family means for every element in Fpn to the d, I give you an exponential sum over the finite field. So the example to keep in mind is Clusterman sums. The parameter is a, d is equal to 1. And for each a, you have the Clusterman sum with parameter a. Okay, so what Deligne proved essentially is that as n goes to infinity, so in this direction where everything is over the same base field, but we take larger and larger extensions of the base field, some equidistribution theorem. So it's kind of a slogan. Let's try and make it a bit more precise. And then I'll give the example of Clusterman sums to make this very, very concrete in one special case. So, so slightly more precisely, so for any family of exponential sum parameterized in this way, so Deligne, following the old formalism of algebraic geometry, so one should mention many other people like Grothendieck especially and so on, but let's say Deligne constructs two groups. Okay, I went too fast. So, so one is a normal subgroup of another, and I call them GRE and GO. That's not very important what they are called. They are naturally given as subgroups of matrices of some size. So some integer non-negative, which tells you essentially the size of the exponential sums, the maximal size. And so here there's a kind of technical condition which has become very frequent. If these two groups turn out to be equal, they are naturally not usually equal, but you can sometimes tweak the sums a bit to make them equal. And if they are equal, there is then a compact group, a maximal compact group in this common group. So let's say in GRE, such that the exponential sums as n goes to infinity, when we vary, become distributed like the trace of G, where G is a random element in the group capital K. And by random element, this means chosen according to the probability measure, the invariant probability measure, the R measure on K. Okay. So this is a very general abstract theorem. It tells you there's always some kind of equidistribution. So there is this technical condition here, which I will come back to later because that's often a bit annoying if you don't know what the groups are, because it could be difficult to check. And it does not tell you precisely what's the equidistribution statement, because obviously that will depend on this group capital K. But it is still very strong, even from an abstract point of view, because it says the limiting measure, the way the traces, the way the exponential sums occur, cannot be an arbitrary measure on the complex numbers. It has to be the traces of random matrices in some compact group, which is a very, very restrictive type of condition. So let's go to the prototypical example, which, so building on the work of Deligne, Katz started computing or finding methods to compute this group capital K in order to find the concrete form of equidistribution. And the basic case are the Clusterman sums. That's maybe the first really interesting really non-trivial case. So let me write explicitly what this means. So you fix an FP, then you look at the extension of degree n, you take a parameter A, which in fact will be non-zero to make things work better here, in Fpn star, and you look at the exponential sum, which is the Clusterman sum with parameter A. So it's the sum of, you have to take the trace from the extension field to Fp to obtain an additive character of Fp to the n, Ax plus the inverse of x in Fp to the n, so inverse in Fp to the n. And in this case, Katz proved that the technical condition is true. So the two groups are the same, and they become equidistributed in K, which is SU2C. So like the trace of G. Okay. And from this, it's a standard computation that means the measure on the complex numbers that appears is the Sato-Tate measure. So the trace of a random matrix in SU2, that's one way of defining the Sato-Tate measure. So I always get the 1 over pi wrong. I don't know if it's 1 over pi or 2 over pi. So it's a measure that's supported on the interval from -2 to 2, and it has a density which is the semicircle density. Okay, and if this measure has mass total 1, this is the right one. Otherwise, you have to adjust the parameter, because I always forget. Okay. I'm not going to say much more on this because we want to discuss other cases. So the only thing to say here is that the two groups, so which are the groups we're going to want to generalize later for other families of exponential sums, they are not mysterious. They do not arise from tannakian categories. So they are defined essentially as images of homomorphisms of groups from some kind of Galois group to GLR. Okay, so you should think of this as some kind of Galois group. It's an infinite complicated group, but it's given and associated to the given base field. And the family of exponential sums naturally gives you homomorphisms like this. And you just take the image essentially. And that gives you the two groups. So there's going to be a subgroup of this pi1, which gives you the other group. And that's why they are not always the same. Okay. So the key point I want to say, the only thing to remember from the point of view of this talk is you have two groups, but they are obtained in a completely standard way. So usually when you define a group in mathematics, well, there are ways to construct basic groups, and then you take the kernel of homomorphisms or the image of homomorphisms or things like that. And this is a construction of that kind. Okay. So this was the situation, the first really general equidistribution theorem, Deligne, around 1980. Okay. Now we skip quite a bit. So this was the standard equidistribution result, and in some sense the same, the only one, until Katz started to think from 2003 when he was asked, in particular by Zev Rudnik, to study certain types of sums which were not of the Deligne kind, until around, well, he's still thinking about it, I'm sure, but his book came up in 2011. So he's looking at families of exponential sums of finite fields parameterized by a multiplicative character. Okay, and again, over extension fields of a base field. So these are not of the type treated by Deligne. Okay, so a priori, these were things that one could not study directly the way Deligne did, and for a while this was completely mysterious what could happen. Now there's one thing here is that for very simple families, you can do numerical experiments indicate that there should still be something similar. There should be a similar equidistribution theorem. So here's, I think, one of the first two examples that that Katz looked at, because so Evans had asked him about it, is the following. So it looks a bit like a Clusterman sum. I'm just going to write the variant over FP, but then you can take the version over extensions of FP. So the x minus x bar has the advantage of making this a real number, as you can check by, this is a real number, by taking complex conjugate. So experimentally, these seem to be also Sato-Tate distributed. When you replace P by P to the N, as usual. Okay. This is computation and that you can do for pretty large values of N, or letting P go to infinity in some sense. And numerically, the experiments are very convincing. And so in the end, so Katz, in his book, so between 2003 and 2011, managed to understand how one could prove actually such theorem. So it's a really remarkable insight that something like this can be done. So something like Deligne works. So there are two groups. So to any family, I should say so here. So for families parameterized by a single multiplicative character. Okay, so single multiplicative character, that's actually important. So there are two groups. One is a normal subgroup of the other. And if they are equal, there is equidistribution like the trace of a random element in a maximal compact subgroup of this group. Okay. So it's really essentially the same statement as the Lin's theorem with these same features, two groups. If they are equal, there's equidistribution, and the limits that arise are essentially of the same kind. The traces of random matrices in a compact subgroup of some GLR. So the R depends on the exponential sums, of course. And in the Evans sum case, so Katz showed that the two groups are the same and are equal to GL2, to SL2 contained in GL2. And so the measure is setotate. So the maximal compact subgroup is SU2. So the measure is the same as for Clusterman sums. Okay. But now, so the proof has two parts, naturally. The first part is to prove the abstract theorem. In the abstract theorem, one doesn't know anything about what the groups are, one just shows they exist. And then to prove a concrete statement like Evans, like the ones for the sums of Evans, you have to compute the group for the given concrete example. Okay, so the second part will come to later, but the construction of the groups to show there exists a group for which the equidistribution is dictated by this group. The groups are constructed so using tannakian categories. So an extraordinarily abstract kind of tool turns out to be the right way to construct the group and then to deduce the equidistribution. I should say that the proof of the equidistribution also then naturally relies on Delin's Riemann hypothesis. So not on Delin's equidistribution theorem, but still on the very general form of the Riemann hypothesis that Delin proved in his second proof of the Riemann hypothesis. So the same one where he proves the equidistribution theorem also as a consequence of that. Okay. So let's maybe take 2 or 3 minutes to try and understand what turns out to explain why we can get a group out of this kind of situation from a very, very abstract method. So in this case, there is, as far as we know, no description with homomorphism, and we take the image or something similar. So what turns out to be the key fact, so as I said, the tannakian description of a group is in terms of its linear actions on vector spaces, 5-dimensional vector spaces. So linear actions of a group G lead to their traces as functions on the group. So the so-called characters of representations of the group. And it's known that in some sense, from the trace, you can recover the representation under certain conditions. And of course, only up to some kind of isomorphism, because there's less information in the trace than in a completely general linear action. But somehow you can kind of almost go backwards. And now the point, one of the key ingredients in the rigorous definition of a tannakian category is that if you have two linear actions, you can take their so-called tensor product, which concretely means that you can multiply the traces. So if you take two linear actions with two traces, the products of these is a new function, which is also the trace of something. So these can be multiplied. So one other way of saying it would be to say that the set of characters forms an algebra. But concretely, that means if you have two such special functions, you can multiply them and it's still of the same kind. And this turns out to be essentially this possibility of multiplication turns out to be crucial to reconstruct the group in the tannakian formalism. So if you have some sets of distinguished functions somehow which behave well multiplicatively, there is a small chance that this could be related to a group through this procedure, looking at linear actions, taking traces, and then multiplying the traces. Okay, and so what Katz observed it's a super simple observation, but it's absolutely crucial. What is the key for him to start thinking and reconstruct a group from exponential sums? Well, is that, as is well known, if you take the product of two Fourier transforms, so in this case, these are kind of Mellin-like transforms of a finite field. So one exponential sum in one family associated to some function t, which could be the Evans function e of x bar minus x bar. You multiply by another one with some other summand s of x, which could be the same or something else. So you have to think of these as functions of chi, parameterized by chi. So this is like the discrete Fourier transform of the multiplicative group evaluated at chi, times another one for another function. Then the product of two Fourier transforms is a Fourier transform associated to the convolution. So this is multiplicative convolution. I don't write the formula. It's not even needed. But so this shows that if you look at parameterized families of exponential sums with a single character as parameter, you can always write by a Mellin inversion or Fourier inversion as in this shape. Then multiplying two such things give another one. Okay, and this turns out to be, it reflects the multiplication of traces of linear actions of some group. And this group is one of the two groups that Katz constructed. In this case, it's the bigger one, the GR, the one that okay. So it's just a very, very short, and of course, from there to actually making this work, there is an absolute gigantic amount of work. But this is really the basic idea, the motivation. Now let me go towards what Arthur and Javier and I have been doing and are doing now. So, so the question we wanted to ask, and I'll give some motivation. So what about exponential sums parameterized by characters not of FP star or not of FP, but of more complicated groups? So, but still parameterized by characters. So a simple example would be a multiplicative and an additive character, but you could think of a tuple of multiplicative characters. So here maybe something like so, and then polynomial in d variables. So this could be the kinds of sums you want to think about. So here you would think of Clusterman sums in general. So these are examples of this kind, and you know, if you think of finite groups coming from algebraic geometry mod P, you could look at abelian varieties. which turns out to also give some very interesting examples. But already, I think the first two cases are fairly natural from the point of view of analytic number theory. So let me say what kind of motivations one can have. So the first is that it's a natural question. And it's also, again, a question where you can do experiments numerically. And if you do the experiments, well, you will observe, again, always the same kind of behavior, some kind of equidistribution, and always with the same kind of limits. So, which seem to be the traces of random matrices. There's another one, which is for tuples of characters. So this has applications to problems. So the variance of arithmetic function in arithmetic progressions over polynomials over finite fields. And here there's a paper in particular by Hall, Keating, Roditi, Gerson, where they use the formalism of cats by specializing to one parameter subfamilies and doing some work. And they needed some conditions which were quite restrictive. So one of our goals was to remove these conditions by using a more natural approach. So what they were doing is they were kind of freezing d-1 of the characters and then just summing over the last one and trying to apply Katz's result for each fixed tuple of the other ones. And that's somehow artificial. Okay, so let me state now the theorem we can prove. Well, so we definitely hope to have this finished in 2021. So for such situations, so what do I mean by such situations? So the characters have to be the characters of a fixed algebraic, commutative algebraic group, connected commutative algebraic group. So for instance, a power of GM would be the thing that gives you a D tuple of multiplicative characters. I don't want to give too many technical details. Then we have the same kind of theorem, except we have a small tweak, which allows us to avoid the assumption that the two groups are the same. It's a tweak that can be applied posteriori to what Deligne and Katz did. In our case, it's nice because knowing when the two groups are the same seems to be, in many cases, difficult. So there exists an integer, and there exist groups. So again, it's the same description as already in Deligne, two groups contained in GLR. So for K, a maximal compact subgroup of the bigger one. So some compact group of matrices. So if you look at the sums, so to be precise, what are the sums? So there's going to be the sums like the characters, which are the parameters. So they are not necessarily just one character, it could be a tuple. We sum over a variety, so a group and the FP endpoints of some group, which could be the multiplicative group to the power D in the case above. And so these are the families, and we have some kind of trace function, which is the thing we put in the middle. So it could be the exponential of a function on the group. So E of f of x over p, where f is some nice function on the group. With some normalization that I don't write down, we put it in the T. So R equidistributed. Okay, and here comes the small tweak on average. I'm going to say what it means, like the trace of a random matrix in this compact group. Okay. So this equidistribution on average is a very natural and simple analytic trick or probabilistic trick to avoid making the assumption that the two groups are the same. And in some applications, this equidistribution on average is just as good as the standard equidistribution. And we find that it helps a lot in understanding what goes on because it avoids this restrictive assumption. So what this means is we average the families over a sequence of finite extensions of the base field. So we sum over the integers from 1 to capital N, and for each of them we do the kind of usual sample with a test function, and this converges to the integral of the trace of a random matrix on K. So for any continuous bounded function f on C. Okay, and SMK are exactly these sums here. So M is the object that gives rise to this T. So it's a trace function of the object M. Okay, so the precise details are not so important. So what is nice to see is, so for any reasonable algebraic family of exponential sums parameterized by the character of, let's say, the multiplicative group to some power, meaning tuples of multiplicative characters of a finite field, there is equidistribution in this sense. Okay, so the average over capital N is the thing that allows us to avoid assuming that the two groups are the same. Okay. So that's a general abstract statement. The construction of the group, of the two groups, is by the tannakian formalism again. The basic observation is always the same. The product of two Fourier transforms over a group is the Fourier transform of the convolution. Over a billion groups, it's a commutative operation also. So using convolution. So the key tool is really this thing. So I don't have the time to go into the discussion of how to do this. It turns out to actually be non-trivially more complicated than what CADS does, because the groups can be of higher dimension, meaning the sets of parameters, and there are still things we don't quite understand on how to make things work equally well as what CADS did, but in principle we have a nice picture with this formalism. Okay, so now let me give an application, and let's go back to the Sidon sets. So we are going to look at the following thing. So we're looking at these fairly simple families parameterized by an additive and a multiplicative character. So I write them this way. So T is the trace function that gives us what we want. So you should think of this as maybe E of f of x over p for some function f, some polynomial f, for instance. So the parameters are chi and a. So these are the parameters. So our theorem applies. So we know there is equidistribution for some group, some compact subgroup K. But the question is, what is K? So as I said, Katz has developed a lot of methods in the context of the Lin theorem to compute the group. He has a few other methods in the context of multiplicative characters. But in general, these kinds of tools are not available anymore. So what we use instead, what one can use sometimes, not always. So one tool is the following. So it's a theorem of Larsen, which I will state very quickly, that if you have a subgroup of UR of C, compact subgroup, R at least 2, and this satisfies that the integral of the fourth power of the trace is equal to 2, then either the group is finite or it contains SURC. So either it's very small or it's very big. Okay. Now, how can we use that? So we can use that because by equidistribution, we can recover the integral of the fourth power of the trace. If you see my equidistribution theorem, we take as test function modulus of z to the power 4. So it's not quite bounded on C, so we have to be a bit careful, but we can compute the force moment of our sums. So let me do it, and I will end quickly. The computation is very fast. So we average over A in FP and chi multiplicative character our sums to the power 4. So the same sums I wrote before. You expand the fourth power. So you had the 1 over square root of P, which was a normalization. So you get P squared, P times P minus 1. Then the sum over X1, X2, X3, X4. The functions in the middle, Tx1, Tx2, Tx3, Tx4 conjugate. And then, of course, sum over A, sum over chi, chi of X1, X2 over X3, X4. And then the additive character of X1 plus X2 minus X3 minus X4 over P. Okay. And you get, therefore, by orthogonality, 1 over P squared, the sum over the solutions of so you get the sum over precisely the Sidon set, which is the diagonal in FP star cross FP. Okay. And now, because this is a Sidon set, this becomes just the sum of the modulus of T of X squared, normalized by P, modulus squared, times 2, because of the two possibilities for X1 equals X3 or X4. And in many cases, think of T as being something of modulus 1. This converges to 2. Okay. So again, you have to think of the situation where T of X has modulus 1, like E of F of X over P, and then you get something that converges to 2. So that means that by the theorem of Larsen, the corresponding group K is either finite, and there are tools to try and show that this is not the case, or contains SURC. what is nice is you don't even need to know what is the value of R in that case. Okay, so I don't have time to give more examples, so I stop here for these general things. I should say that there's still a lot that we don't know how to do. There are very natural examples of families of sums with this kind of two parameters where we cannot compute this force moment, although we certainly suspect or even sometimes can prove by other means that they are equidistributed. So it's a theory that's just beginning, but the combination of the really concrete, the combinatorial with the Sidon condition, and the and this formalism coming from very abstract algebraic geometry, I find quite appealing. So thank you for your attention.
Thank you very much. So, question time.
Hello. So I have a small question.
Yeah.
So in the result of Ivan, you mentioned your X is whole multiplicative group. Then the exponential sum is equidistributed with parameterized character. So if you restrict the X over the any subgroup, still the equidistribution holds.
So which kind of subgroups do you mean?
Any multiplicative subgroup, as you fix your X is F star P. So if I fix X belongs to subgroup of F star P, result of events.
So so if you mean in the summation I replace the summation of a group by a summation of a subgroup?
Yes, yes.
So so this is not of the same kind. So if so in this case you obtain sums which are naturally parameterized by the characters of the subgroup, because you're just summing the, if I understand correctly the question. So you're then summing you're summing over the character.
Your variable X is subgroup of F star P.
Okay, yeah. So if you're thinking of like replacing FP star by a small multiplicative subgroup,
right?
Okay, yeah. So then this theory unfortunately doesn't tell you anything about it, because the group on which we sum still has to be an algebraic group. And so in FP star, it's either the trivial group or it's all of FP star. So because we rely on algebraic geometry, we need the groups on which we sum to have this kind of algebraic description. So yeah, it's a very good question actually. Yes. So I mean, so Bourgain, for instance, did a lot of study on various exponential sums on small multiplicative subgroups. But these kind of methods typically cannot tell us anything if the subgroup is small. So if the subgroup is large enough, you can detect it by multiplicative characters, and you will get the same kind of restriction as in the Polya-Vinogradov type conditions. So if let's say if you look at a subgroup of the multiplicative group of size a bit larger than P to the 1/2, then yes, there will be a good theory, a good equidistribution theory. But if you take something, let's say of size P to the 1/4, then it should still be true, but we have no tools to study that.
Okay. Thanks. Thank you very much.
I have one question, if possible.
Oh, hi, Guillaume.
Yes.
Hi.
Yeah. So do you have any idea about analogs of Sidon sets which may occur when you compute higher moments?
Yeah, so typically you would want to find, so let's say you want to compute the 8th moment, which is very natural because it excludes the possibility of the finite group in Larson's theorem. And you need to find 24. So you need to have sets where if you have 4 elements with the same sum as the 4 other elements, they are permutations of each other. So that's where you get the 24. So one example of that kind is if you take a curve of gonality at least 5 and you embed it in its Jacobian, then you will get this kind of thing very naturally. It's trickier to get out of, let's say, with FP star cross FP, it's not the case, for instance.
So we had 2 excellent questions. Let's thank Emmanuel again.
Thank you.